All right. Hello, everyone, and welcome to Handmade Hero Show, where we code a complete game live on stream. You may have noticed we've got a Kickstarter going right now. For those of you interested in comics, you might want to check it out. Anna and I have been working on it for the past year or so, and there's a print edition up now. So there's a banner on the Handmade Hero page, so if you visit the Handmade Hero page, it's pretty easy to find. We're going to jump right into the coding today. We have a bunch of work we can do now. We set ourselves up to do some optimization of our rendering pass, well, specifically the lighting, the raycasting in our rendering pass. And we actually set ourselves up to call the entire path, actually. So one of the interesting things is we can now also work in an isolated fashion on optimizing the texture processing if we want to. So that's all pretty good stuff. So we now have this HH Light Prof, and if we actually run that, you can see if we go to the Handmade directory and we have like a debug dump here that we dumped of all of our lighting data, which I think is included right now. I don't know if it's included in the GitHub. It's at least included in the, it's probably included in the GitHub, but it's presumably included in the zip files that you download from Sendowl, or you can take those dumps yourself using the source code, depending on how you're doing it. But once you get those dumps, we can actually run our HH Light Prof executable. It will load those dumps. It will do a Texel match to see to what extent we're agreeing with our previous results. So, for example, if we look at this number and it's relatively low, we're in fairly good shape. And then it will tell us how long it took to do things. And you can see here how many seconds elapsed total. And basically what this is doing is it's just taking the thing that Handmade Hero does for lighting every frame, and it just runs it a ton of times. So it runs it for, 7 seconds, and it just keeps running it. And the reason for that is just because it runs so fast normally, because, anything that has to run at 30 frames a second or 60 frames a second is probably already down to the point, even before we optimize it hardcore, where it's, it's running fast enough that it's hard to time because the variance that you're going to get in there is a little bit too much. So we're just running it lots of times so that we can kind of smooth that variance out a little bit and get somewhat consistent run times out of it, so we can see how our changes actually affect things. So what I'd like to do is I'd like to take a look today a little bit more at just reducing the amount of computation that we're actually doing here. There's a couple of different things that we can do that we haven't really looked at yet. And so if we look at how our lighting solution's actually working, we can actually go to the raycast and see this right now. We did the work already of splitting it into two types of loops. You can see those loops operating here. And there's a whole bunch of stuff that's not immediately clear out of it. I hope that most people watched last week, because it's going to be kind of hard for me to explain what's going on here if you haven't seen it all. But what I can try to do to bring you up to speed a little bit is there's two sides of the loop in the Raycaster. And one side of the loop, which is actually represented by the first part here, is actually the part that does the raycasting against our actual, volumes we hit. So this is actually the part that does all of the raycasting that can actually produce results, right? But then we have another side of the branch that's here, which is basically the thing that does all of the raycasting against things which categorize space. So this right here is something that categorizes, it looks to see which parts of various structures you're actually going down, right? And so this allows us to take our spatial hierarchy and cast it and figure out which parts of the spatial hierarchy need to be examined and which ones don't. And so it's not really producing actual ray intersections. What it's doing is testing to see whether the ray hits a particular region so that we know whether we need to look at the things inside that region. And that's recursive, right? It doesn't actually use functions to recurse. It actually just keeps a little stack, but it's still doing it recursively in the sense that it looks at something and then goes, oh, if I hit that, I'm going to put more things onto my stack to process, right? So that's the way this is actually working, and what's interesting about that is it means that we have two totally different, right, specific ways that we're doing our testing, and they don't necessarily have much to do with each other. So if we go look at something like the lighting box structure, what you can see is that if you take a look at this here, we have this lighting pack, which has this information in it, right? And then we have this stuff, which has the P, the radius, and the ref color. And what we know, at least at the moment, is that it's unclear to us that we ever actually care about, like, what we're actually storing here, the box P and radius. What you can see is that more or less all the time we actually use that, we expand it to box min and box max. And the only time we ever actually use the P and radius is to store those to be used finally at the end when we actually know what our hit is. And so we could trivially reconstruct those things by just actually storing min and max. And so the first thing we may want to do, just to get rid of this cruft, like this stuff that's happening here, to get rid of this cruft, what we might want to do is let's just take the simple step of saying we're just not going to do that anymore. We're going to store box min and box max, and that's it. And also, while we're at it, let's take a look at how this thing is working. Ref color here also is the kind of thing that we could look at and say, you know what, that's too big. We could easily eliminate some of that by stuffing that into the lighting box pack as a U32 or something like this, right? That's just the color value. That's like RGB and like a scalar or something like that. So it turns out that like this could also be optimized away in some way that would make a lot of sense too. So there's other things here that we could do. But for the time being, I think the first change I'd like to make is just get rid of extraneous computation, because as we're like working through this, there's really no sense in having extraneous computation. And we know that both sides of our branch are doing this extraneous computation. So it's not like this is going to be something that we will, like if we decide to separate these two branches out into completely different routines or completely different passes, it doesn't really matter because both sides want this change. So it doesn't seem like there's any downside to it to me, right? So what I'm going to do here is say, let's pretend there's a box min and box max here, where we just say, okay, we're going to go ahead and take this to do and take it seriously. So instead of the radius, we're just going to get rid of that, right? And we're going to do everywhere that we were previously filling these out, we're just going to take the P and radius and do exactly this. So we're going to say, look, the box min is going to be the P minus radius, right? And we're going to say that the box max is going to be the P plus the radius. And that's what we're actually going to store. So when the person actually gives this to us, we're going to store it that way. Now, you may ask a question, and it's a perfectly legitimate question. Why does it matter where we do this? Like, if we're gonna have to do this expansion anyway, like, don't we have to back propagate this to the people actually calling us or anything like that to order to do the savings? The answer is no, because remember, every single ray we trace has to do this to every box it encounters, whereas this only happens when you create the box itself. So when we actually push the occluders on each frame. So this happens once per box per frame. This happens once per box per ray per frame. And since we know we have thousands, tens of thousands, potentially hundreds of thousands of rays, there's an extra multiplier of 1,000 or 10,000 or 100,000 on here, depending on how many times this box gets hit. So the difference in multiplier here is massive. So doing it once here versus doing it thousands or tens of thousands of times here, that's the savings I'm looking for, right? So it's like, it just seems obvious to me that we just want to get rid of that cruft. Now, it may not have much effect because it could be that this isn't the slow part, but again, one of the things you have to do when you're optimizing, since there's so many variables involved, is just don't do anything obviously stupid. Get it out of your way so you just don't have to think about it anymore. And this is a clear thing we can just get out of our way, right? So what I'm going to do now is just get rid of that so that we're clear about that. And then from then on, now here we can just go, all right, every time we were doing this, we can just always use those other values. So instead of rect center half dim, I can do min max and just, you know, create the rectangle out of that pretty easily here. Same thing here, rect min max. You know what? This actually looks like it's just using these, since we don't need the extents value here at all, it looks like. We probably don't even need to do that, but you know, okay, whatever, you know, it's fine. So inside the box min, box max stuff here, we'll just do it like this. And then we just need to update our actual lighting routines to use these, right? So you can see those happening there, and you can see us doing some of the work with it in our actual tree construction. So this, again, is going to be something we're going to have to work with as well. So let's go ahead and do the easy part first, which is this routine here. So in here, we've got the box P and the box radius, and we don't actually want those anymore. So we're literally just going to load up we're going to change what this is to just saying, look, we're going to load these directly out of their two corresponding members there, and we're not going to construct them anymore. So if we just do this, we should find that now we don't have any need for those other than the place where we store them for use later. And so in here where we actually store them, where we've got the hitbox center and that sort of stuff, what we're actually going to do here is say, look, hitbox min and hitbox max. So we're going to store the min and max. So again, exactly the same code, but we're just changing it so that now it doesn't use those values. Okay, so now all we have to do is, oops, hitbox min, hitbox max. Now all we have to do is at the end where we actually use these, anywhere that we actually needed the radius, so in places where we actually needed to use that, we can reconstruct it. Now, eventually we probably want to do this. It's possible, like I think it's likely we could actually make this work by, instead of using the position and the radius, by using something else. But in this particular case, I don't really care about that, because since this part of the code is so rare, like this happens only after you've done all the loops up here, only one time. It's pretty free for us to do any calculations we want to do here because it happens so infrequently compared to everything else. So I don't really care about this right now, so I'm not going to spend much time on it. I'm just going to recompute the hit center, although wait, does it even need that? So it looks like it only needs the radius. So if it only needs the hitbox radius, then that's fine. So all we have to do for that is we're just going to do a multiplication here, and what we need to do is subtract the two and then take half of it, right? So we have the box max minus the box min. That gives us the diameter, and then multiplying that by a half will give us the radius. So we can just recompute that, right? Sorry, it's hitbox min, hitbox max. So it's pretty trivial. Oh, there it is, hitbox center. I'm like, I thought we needed that. And I was like, we should have needed that. So to do the hitbox center, again, pretty straightforward. It's the same thing. And again, I'm not thinking about these at all. I don't care about how fast this part runs because I just don't think it's going to be particularly relevant to us. So then it just leaves us, I think, with just this one routine that was made to work on other kinds of bounding boxes. And I think, so it's just the spatial partition stuff that's necessary, I think. Yeah, so basically we're just looking at two things, split box and then the stuff that calls split box, right? Now it looks like this one's actually pretty straightforward. It looks like in this case we can just use different calls and it'll just work. So this routine looks like it's pretty straightforward to port. In this case we're just doing a rect min max here is all we actually need. So there's our box min. There's our box max. And this is much like, what was it, in the, I guess it was in lighting computation. Where were we actually looking at this before? Let me just do a quick search here. Box min max, or rect min max. Yeah, okay. So in get light leaf for P, you can see was the other place we were doing those rect min maxes, right? So in through here, yeah, but that's about it. So yeah, in here we can just do rect min max, and this is just to build up the total bounds of the lighting. So again, it doesn't really matter. We're just unioning these two things together. In here, we are pulling those out as a P and a radius, but we could just pull them out as a min and a max instead. So that should be relatively straightforward as well. We can just do like, you know, get min, get max kind of a thing, which is just a direct access. So it's literally just this, I believe. Am I right about that? Sorry, we don't want to look at this function. There we go. Yeah. And so it's, again, really, really simple. We don't actually use this root lightbox stuff anymore, and so we're probably going to pull that out, but I've been leaving it in just in case we decide we want to try some light shooting approximations where we or some biasing towards lighting in the future. I don't know if we want to do that. We probably don't. But I just wanted to keep that in there in case we find we want to try it again. So yeah, it looks like our errors are now isolated entirely to the split box routine. And since now we're only looking at the split box routine, we can concentrate on what actually needs to happen here. Now, some of the porting is exact, the same sort of stuff we were doing before. So box min, box max here, again, just really simple min maxing here, right? So instead of getting the center and the P out, we just do it this way. So when we do the bounds A, bounds B, we're really just, producing those mins and maxes directly. So this, again, if anything, this is actually just more efficient than it used to be, because now we're always using mins and maxes instead of using center radiuses, which weren't ever really what we wanted in any of these routines as far as I can tell, right? And now we're literally just down to a couple things, which is the inner product with the actual center of the box. Looks like the only thing that will be less efficient. In here, again, rect min max is quicker, so we can just do that. And that, again, just uses the box min, box max. Right? So I think that's basically it, and all we're left with now is the fact that, look, we're trying to classify the centers of these things. You can see us doing that here. And so we just need a way to compute box P, and really that's just getting the center, right? So all this is right here is just, look, box P in our case, and we don't really even need to do this. We can just do it here. We can just say, look, this parent, this thing here, we've got a box min and a box max, right? We've got a box min and a box max, and we just want to take the middle, right? So that's it. We're just getting the center of that thing, right? And the same would be true here. So instead of parent box, it's just box. But in theory, that's all we need, right? At that point, we've gotten rid of anywhere, and it depends if we introduced any bugs there, but that's really all we needed to do. So we can see probably pretty easily if we got any errors by just looking at what the actual error is. You can see I must have had an error there because, oh, no, we have to recapture now, actually, now that I think about it, because we've changed the storage format. So we're going to have to recapture our dump, which is unfortunate, but that's just how it's going to be. We can't actually see to what extent that helped us. Well, we could, though. Now that I think about it, we could do that. So here's one way we can still use the same dump. When we load this thing in, so when we actually do our debug load, so in LightProf, when we load in this information for the debug load here, so this stuff right here, what we can do is we can quickly do a debug pass that just updates those pieces of information. So in here where we do, right before we call internal lighting core, right, we can do a quick sweep over all of the boxes in the system, and we can change them. So we can just say, all right, we've got a box index. The box index is going to go up to whatever the box count is, right? So we just go through all of the boxes, and we take each lighting box and we transform it, right? So we can say, okay, for whatever box we're on, we take box min and box max, and we compute values for those. And all we have to do is recognize that box min, the value we loaded in is actually going to be the P value, right? So all we have to do is say, look, here's the, if this was, this was the old P value, right? In fact, I can just do it this way. And this was the old R value, right? Is that clear? Hopefully that's clear. So then we can just say, okay, the old P minus the old R, that's going to be the radius, and the old P plus the old R, that's going to be the new max, right? And so now we should be able to debug this without actually having to take a new capture, right? And if we look at what happened there, you can see now we actually get the same results, right? We actually get the exact same results. And what's nice is, as an added bonus, we actually got faster, right? So here's the old speed that we used to be running at, 7.15 seconds for the test run. Now it's down to 6.7 seconds, and all we did was change the data storage format, right? That's it. We didn't do anything else. I'm going to put a to-do around this because once we do a new capture, we don't want to do this anymore, right? So we only want to do this while we're using old captures. So we don't want to do this once we do new captures. So that's fine, right? All right, so again, really great, cheap optimization for us there. All we were doing is removing cruft, right? We worked backwards going, look, we optimized this routine at least somewhat, and we can see that we never really care about the position and radius in the inner loops of this thing, so we don't really want that to be primal, right? We want something else to be primal, which is the box min and box max, so let's just do that, and then in the cases where we think we might want the radius in the center, we can just regenerate them because that's only happening at times that aren't performance critical. Right, so it's just shifting the data storage format so that we're not doing spurious computations in sort of more specific scenarios here that are expensive, right? So there's a lot of other things we could choose to do here, and they start to get kind of squinky particularly fast. But there's one thing that I do want to know. There's a couple of things that we've tried. So we took a look at this routine before, and one of the things we were looking at is whether branchless, whether making this routine work branchlessly was a win or not. And one of the things I realized was because our trees are effectively binary trees, they split the world in half each time, this loop is not really a loop, right? Every time we look, like, the way to look at it is, this is not only a this branch is not only perfectly predictable, it happens every other time, but it's also not really a loop, meaning we're just loading two things, right? And one of the really stupid things about this is we don't actually need to do two tests. We could just do one test and know what we're pushing on. Because all we really need to know is, does this particular ray cross both regions that this is split into, or just one, right? Or neither, right? There's basically three cases. It crosses 1, it crosses 2, it crosses 0. Or 0, 1, and 2, right? And so we have a lot of issues that we want to start thinking about now in order to speed this part up. And this is the part right here that does the work that we actually care about. And I'm trying to think of how to explain all the issues here. So we have three main points we now have to start looking at and pushing on. Point 1, how do we actually want to store our tree? Right? Because what we did before is we just stored it in the lighting box structure we already had, and we don't really know, A, if we want that, meaning, do we want to do it that way or not? Do we want to store some other struct that's separate? 2, what does this tree want to look like? If it's a KD tree, like right now it's a KD tree, that's what it is. We're not actually storing it as a KD tree. We're storing it as if it could be an n-ary tree, an n-ary AAB tree, basically. If we're going to do a KD tree, if we're going to decide right now KD tree is what we're doing, and we're going to go forward with that, we should just make something that's purpose-built for KD trees and doesn't have a whole bunch of extra crap in it, right? So there's that. And then finally, do we actually want these in the same loop or not? Because there's two different ways we could do this. The way that we're doing right now is oscillatory. So we go down sort of depth first, and we process some hits, then we pop up, process some more hits, and so on, right? So it's a depth first walk of this tree. But we don't have to do that. We could do more of a breadth first thing where we do all of the culling first, build some kind of a list where we go through that list, right? And we could do something like that. And right now, I don't know which of those two things we actually want to do. So I think what I need to start doing now is investigating how is this actually, what's the most efficient way to actually use what we have here, right? So what's the most efficient way to stream these pieces of information out, right? That's what I actually want to know. And so I think I'm going to try constructing what we have right now. So without touching really anything else, I want to see what happens if I change the way that we're structuring these loops, right? And I just want to get a feel for whether or not we can make a market improvement by, for example, separating these into two different loops that are unrelated to each other. Okay, so that's all we're doing. And the way I'm going to do that is I'm going to essentially keep more or less what we have here. And I'm just going to maybe if zero out one of my so it's going to be kind of tough to test, unfortunately. Because we're going to have to make some decisions even just to test it, and that's unfortunate. But I just want to see what the difference is if we just change it into two loops. And so what would happen is, as we do our loop here, we would just have a thing that allows us to do a C move onto a totally separate stack. So, right, that's all we're talking about here. So basically, what I want to do is, in the lighting work structures, basically, there would be a scratch array that can be used for streaming so that you can basically, here, I'll show you. So I'm going to go ahead and go to the lighting work structure. And in here, what we're going to do is say, in addition to all this other garbage that's in here, we're going to take a little bit more off the big pad. So we're going to subtract another 8 from that and get down to give us like space for another pointer, right? So we're going to have big pad is not really a big pad anymore. It's more of a small pad. And in here, we're just going to have a lighting stack thing that we push on, right? So we already know we can represent all of this by just having lighting box pack. So what we're going to do here is we're going to say, look, there's a lighting box pack, and the lighting box pack is like the scratch space, right? It's just a scratch array that we're going to use for whatever stack random crap we need here. And we're going to assume that whoever is running this thing is going to allocate enough space here so that we know that we won't run out, right? And that may be a lot of memory, actually, but it doesn't matter as long as we don't touch it, right? So what we're going to do there is just say, okay, so during the course of the allocation of work units, so, when we're actually creating the work units, we're going to want to assign them to some memory, right? So in here, where we go through and we zero out the struct, what we're going to want to do is stop this zeroing. So we don't want to do this. We want to be able to leave in certain values that are going to persist. So if you look like diffuse atlas and spec atlas, work index, entropy, these are things that actually need to get set. Solution does not, right? So solution doesn't need to be set. That can be set outside, and so can the scratch space somewhere. Yeah. So the stuff that actually wants to be zeroed is like total casts initiated, total partitions tested, total partition leaves used, and total leaves tested. And we may change those stats in the future as well, according to our needs, right? And so what we want to do here is we want to set these up somewhere else, right? And we want to go ahead and initialize all the things we might initialize here. And so we're going to need to initialize the solution in the scratch space. The scratch space is going to be something that we malloc out that's basically like lighting box pack structures. And it's just going to be like the size of a lighting box pack structure times some number, right? And so what we want to do is, before we get started on anything else, when we're in our actual HH Light Prof, and we'll have to backport this into Handmade Hero as well, if we end up keeping it. If we don't, then we don't have to. Then what we're going to do is, when we do our setup here, so when we malloc this nonsense here, right? What we're going to want to do is go through the like alloc work count, basically, which is, we set it to this. We're going to go through the alloc work count, and for each of these lighting work structures, we're just going to go ahead and set these values. Now, we want to know, like, what's the maximum, max box, or the max work stack depth, right? Like, how many of these are going to be? And we're just going to say, look, it's possible that every box gets pushed on. I mean, sure, right? I don't care. So we're just going to say, look, for every one of our work distribution units, we're just going to say that we have a max work stack depth, right? Now, the problem with this is it's not quite exactly what we want, because there's more of these than there are threads. So what we really want is one per thread, and the problem is we don't really have a way to express that at the moment, right? So this is not the best possible thing we can do. I'm just going to put a to-do here on that. And the problem is that we don't really have that concept in our system at the moment, I don't think. Now, I could be wrong about that, because I think we actually do have... In fact, maybe this is all a waste of time what I'm doing. Maybe we actually already did this. And if we did... Oops. But let me just see. Where is our actual thread work stuff? So, yeah, we didn't really do it, right? As far as I can tell. Because when we call through to these things, or maybe we, well, here's the type def. Yeah, so we pass like a work queue, but we don't actually pass any other information, right? And that's kind of a mess up, that's kind of not what we really want. And inside, like, whatever the queue entry point is, so, like, for whatever our actual work queues are, we probably shouldn't have done that. When we look inside, like, Win32 Handmade, and we go down to, like, whatever the, like, So if you look here, we've got our create thread, and we have our do worker work nonsense here, right? So in our Win32 make queue, where we say like we're going to make one of these thread procs, and we look at the thread proc, you can see it here. What it does is it calls this Win32 do next work entry. You can see that sort of doing a call here, and it does the callback on the queue. What we really should have done is given this, whenever you call someone back using the callback, you should have given them an arena, is what should have happened. So, there should have been something that looked like that. On the thread, there should have been an arena. And so that's just a screw up. And I mean, one of the things you have to remember is Handmade Hero was started, and a lot of this stuff was done like several years ago. And I've done a lot more multi-threaded programming since then. And so, if it was today, this system would look a lot different because I have a lot more experience and I would not have done some of the things that I did. So, this is just like experience talking, right? I can tell you, you definitely want that if you're serious about multi-threading. In Handmade Hero, we're not that serious about multi-threading. We do it to do some of the heavy lifting work, but we don't really multi-thread that much. We don't really need to. But, if you are, you need there to be a scratch arena for each thread because you want threads to not talk to each other about memory management. Every time a thread has to do memory management in a way that another thread can see, you're just locking up your threads and it's bad, right? So we're going to leave this like this for now, just because we don't have per thread arenas. We should. And so that's something you can think about separately. Anyway. In here, we're going to create this scratch space, and the scratch space now can be used. I'm going to call the HHLightProf just to prove that nothing changed, but we kind of knew that because we haven't actually put this change into place yet. So if we now go up to see in our raycaster, if we start to actually use that information, then the first thing I could do, for example, is this box stack information here. I could, for example, or should be able to just do something like this, where I just say, all right, instead of a U64, right, I could do this, where I say the scratch, what is this called again? Scratch space. I should be able to use that scratch space here where I just do a cast of the U32. And the box stack is now, and let me see if I ever take anything weird about that box stack. I don't. So now we should be able to run this without crashing and it should work properly. And basically all that's doing is using that scratch space, right? And I'm going to undo that change almost immediately because I don't actually want to use that scratch space. That's not the goal. I just wanted to make sure I had some scratch space there. So this box stack is probably fine to use exactly as we were. So the only thing I'm doing here is I'm going to say, oh, hey, by the way, we're also going to have another one of these doodads here where we say, all right, there's like a different U32 stack here that we're going to use. Also, I assume we CT assert this? No. I'm going to assert that the lighting box pack here is the same size as U32 because that's just what we're doing, right? That's required. Anyway, so in the U32 star here, what I want to do is I want to load up that, that work struct we have, the scratch space. And I want to call this like some other thing. So this is, instead of the regular box that we were doing, this is our like leaf count, right? And this is our like leaf stack. I don't know, right? Or leaves. And so what we're going to do is we're just going to stream our leaves out into the scratch space. That's all we're doing. So we're going to pull this routine out, right? We're going to say, look, this is not going to happen anymore, okay? And so instead of, instead of doing what we were doing there, we're going to do something different, right? Now, because I can run these two in line, I'm actually going to do that. So what I'm going to do instead is I'm going to say, all right, since we have the ability to run both of these, I'm actually going to do an if 0 here and literally take like this entire thing and copy it, just so I can flip between them pretty easily if I want to, right? And again, I wish compilers made this sort of thing easier. They don't. Like, programming in general kind of sucks because stuff where you want to do A/B testing is so poorly supported pretty much everywhere. It's just annoying. But, what are you going to do? So what we're going to do here is we're going to get rid of this loop, right? So this one's going away. And instead, we're just going to have just this one. And then we're going to have a totally secondary pass that happens completely separately, right? And so you can see what I'm going for here. So what we're going to do is we're going to break up these two loops. The first loop here is going to loop over the stack like it normally would. So this is working exactly as you would expect it to work, right? So nothing weird happening there, right? Whereas this one is going to do streaming, so it's going to just like loop over the leaves, if that makes sense. And there's some things that are a little bit confusing about this, which is that I don't know when we exactly want that to happen. Like, I don't know to what extent we want things pushed on in like a sane order, and to what extent we don't, right? I think what we probably will want to do long term is when we actually sort these boxes in the actual startup routine, we probably just want them so they're already sorted, so that you don't have to do this indirect reference, if that makes sense. But it doesn't matter. Anyway, so what I want to do here is I want to loop over the leaf stack here, reading out each leaf and running over each of the leaves in turn. So in here, we're just going to say, look, what's our leaf index? What's our leaf count? And then for each of those, I'm going to grab out the pack. And this is just going to come from our, what did I call it, leaves? So we're just loading these out, right? And I guess this is called entry. So we're just going to load these out and process them in order that they come. So now we don't have that test in there. We do have this kind of annoying test, which is we don't know how many of these there are going to be each time. And so the thing I'm not sure about is, do we want to unpack these here or do we want to unpack these here? And I don't actually know, right? That's just, who knows? I have no idea. So then if we come up into here, what we need to do is we need to go ahead and take a look at this part of the routine where we're pushing things on. And what we need to do here is we need this to be predicated. So this part here we're not actually using that part. We're using the top part here. So we're using this part, right? And so in this part of the routine, what we need to do is we actually need to do an if on this. And we need to do like a switch on it, right? So we want to take what we're going to pack, right? And we can grab that this way. So we want to take what we're going to pack, and we're going to pack it into one of two places. So either we're going to pack it into here, and we can dispense with this because we know these CMOVs are not actually being done, but, you know, oh well. So what we need to do is we need to take that test where we say, look, is this going to be a leaf or is it not going to be a leaf, right? So we basically want to say, all right, is this box, is this thing a leaf container or isn't it? If it's a leaf container, we actually want these the other way around. If it's a leaf container, we need to go ahead and push it onto our leaves. And if it's not, then we don't, right? Oops. There we go. And so all we're doing is breaking these loops into two passes. That's all I did, and hopefully I didn't screw it up, right? And it looks like I did, like that's wrong. So I've got some issue here that I got to go address. So the timing is going to be meaningless because we've got an error. So let me just see if I can correct whatever mistake we made there. And let me take a look at it. So if the box we're about to pack is a leaf container, we push it onto our leaves, right? Like so. And if the box is not, then we push it onto the stack that we're using at the moment, right? And then we loop, and then we continue looping, right? So this thing keeps going at that point, right? And that's while the depth is valid. When we get through here, we go through the leaves one by one. So this should go through all the leaves. We load each one of the leaves. Well, we're loading actually the thing right above the leaves. We go over each of the children, and we produce the values for it. To be honest, I guess I'm not sure what I screwed up there. That seems sane. So What did I mess up? While depth greater than 0. So this should not have changed. Like, it's still accessing the box stack exactly the way you would expect. It's weird that I wrote those two different ways. Should probably not do that. Let's try to be a little more consistent. There. So, in theory, this should just run exactly the same way as it was before. I mean, I don't see any reason why that would be different, right? The leaf count gets incremented and we pack into the leaves array as we go. And that seems just like what you would expect, right? We didn't touch this branch. Gosh. Yeah, I don't really know what we did wrong there. I mean, it seems pretty straightforward. And, you know, I can eliminate this code out of this branch for now because we can always cut and paste it from above if we want to try it. So it's not like we're going to lose that, right? But I mean, that's the whole routine, right? So we come in here, we just go through the box stack. We push on the leaves for every time we would have put one of those on our own stack. We don't do that. And then in the leaf index run case, we just run through all the ones that we have. Yeah, what did I mess up there? That's a puzzler. Because the total error should be 8 and it's 13. And the max textile error got high. Like, it's just wrong. So you can see that it's not actually doing what it should be doing. But why? I'm assuming nothing else got touched because I'm assuming if I re-enable the old case, I should get right back to the valid version, right? And I do. So it's only the difference between these two cases. If entry is light leaf container and is leaf container. Oh, wait. Hold on a second. Am I doing this right? So I load an entry. Well, no, I think I am. Because it was going to test this before to determine which one of the loops to do. So in theory, this should have worked, right? Because as long as it was a leaf container before, now this should properly pull out its children. I might have stepped through this. Yeah, I don't, there's a subtlety here I'm not appreciating. Where I've done something stupid, but I'm not sure what the stupid thing relates to. It doesn't look... Oh! Duh. To state the obvious, I need to actually check to see whether I need to push. If I don't need to push, I don't do these things. So, yeah, I was only checking the should push in this case. So, I guess that's the obvious error. I was pushing all of those on all the time. Of course, I guess that means technically I wasn't producing an error so much as I just wasn't using the early out conditions that we allow. So, yeah. So that was definitely wrong. Let's see if anything else is wrong here. So that's still not right. At least it doesn't look like it. Right? Because that compiled correctly and we still have the error. Oh no. No, that's right. Is it? No. So that's still wrong. Because that's our max error per texel. Right? Normally. And we're getting a different max error per texel now. So we still have something wrong. So we do should push. We look to see whether we need to push. If we do need to push, we check to see whether it's a leaf or not, and we push it onto the correct stack, right? Leaf containers go here. Non-leaf containers go onto our box stack. And in either case, we're just pushing on the information that we need. Again, totally puzzled though. I have no idea. I don't really even understand why that can possibly be wrong. I guess I would like to assert this potentially. Like every time we pull one of these off, let me just go ahead and do an assert here. Because that obviously should be true, but I mean, let's make sure it is. Yep. So we're only getting leaves in our leaf loop. And so the only thing that I guess could be wrong there is we're not descending down some boxes we should, or we are descending down some boxes we shouldn't. I guess. So in the original routine, when we pulled one off, right, we just needed to know which of these two we were doing. Seems straightforward enough. We then are doing the exact same loop, like this is identical, right? Oh, sorry. This is identical. I mean, that all just seems fine, right? We do a should push, and if we should push, we push onto one of the two stacks. Otherwise, we don't, right? And then we didn't even touch this routine. This version up here. Right? That's just exactly the same. We didn't even modify it at all. It's operating 100% the same. So how did that change? And like, I don't feel like floating point error is implicated here, because you can see that the maximum error per texel is like very different. It's 10 times higher. And while, you know, it's never obviously true that I mean, could it be possible? Sure. But is it likely? No. Right? It's much more likely that there's a bug in these two. So let me go ahead and see what happens, I guess, when we look at the decision list between these two. Like, I mean, let's, I guess, try to look to see what is actually happening in terms of the leaves that are tested and why we're getting certain sets of leaves tested in one and not the other, right? I mean, I don't know what else to do. Unless chat already found it. Did chat already see it? No, doesn't look like anyone did. It's a bummer. You're supposed to find these typos for me. The while depth loop doesn't wrap the second loop. Yeah, but it's not supposed to. right? The point of this is that this while depth loop produces a second count, which is leaf count, and then this runs through it in one pass. So it's not supposed to be wrapped. This is supposed to generate all of the leaves. You know what I'm saying? But it doesn't. And so, I don't know. How is that able to produce a totally different thing? Let's take a look at, let's just stream out. I mean, right? So let's just stream out what boxes we're testing. I can't quite do that in here, can I? So here's what I'm going to do. I'm going to add some macros because everyone loves macros. And what I'm going to do is I'm just going to stream out which boxes we were testing in each case. So I'm just going to have a thing called like record leaf box, and I'm going to pass the box. And then I'm going to have record partition box and pass it there. So in both cases, I'm going to just record, and I'm going to do this in the secondary side as well. So same thing here. And I'm going to record the leaves, and I'm going to record the partitions in both cases. Now, what I'm going to do at the top is I'm just going to say, look, if nobody has defined these things, then we just don't do them. Right? So basically, like, normally you compile it, those things just disappear because they don't do nothing. However, instead, in the HHLiteProf, what we can do is before we do anything else, we can go up here and say, look, let's define the macros in this case to be like an printf or something. You know what I'm saying to you? To like leaf box out. And partition box out. See what I'm doing here? And so I'm just going to stream out those box indices. So this way we'll just print out all of the box indices into files that we can then diff and see what the heck is going on here. So all we need to do is create actual file handles for those. So like, you know, I don't know if this is going to work. I think it will. So like right here. And I guess I can actually do this. So now we will actually compile in sort of a debug sync that can just send all this crap out. And what I'll do is at the outset, like when we actually start, I'll just open up like, you know, some of these where we're just like, yeah, leaf box out equals f open. Actually, I guess these are not binary. Some files. So this is going to be like leaf box traversal dot text and partition box traversal dot text. And then we just have a nice, quick and dirty way to make those work. And I can even predicate these. I can just say, look, if like this thing is defined, go nuts, right? Oops. There. So now when we run this thing, we should get a dump file like of those outputs. So they've been streamed out and there's just gigantic, huge files. Like they're going to be massive, right? Of just like thousands and thousands of traversal integers. And I guess the leaf box ones, well, in theory, this should actually produce the exact same results, I think, in both cases. I also, now that I think about it, we only want them from one run. So I probably also want to do this. I only want that first one. All right, so there's our two text files. Like I said, they're just giant lists of integers. That's the order of the boxes that were tested. And now we can see, like, is it just totally weird or is it roughly the same and there's just a few differences? So what I'm going to do is that one, if you remember, so if we go to the raycaster, it's in here, you can see that that was the new way. So like if we rename those files like these two here, this is like new. And if I do it again with this if in, now we've got the old ones. So, oops. And in theory, we could use, I think we use meld for this normally. I think that's the diff utility we decided to use on stream. So in theory, like I should be able to compare those files and see like how similar they are, right? Like this is just to give me some idea of what the heck is happening in there because I have no idea. Oops, that was not the file I wanted at all. So let's start with the partitions because that's actually the part that I'm most interested to see. So old partition box traversal and then new partition box traversal. Compare. So here's the comparison, right? I don't actually know how to use meld. I use beyond compare normally. So, I mean, that seems to be suggesting they're exactly the same. Is that what that's saying? But they're not. What's going on here? So, does this utility work? Like, what the? I want to diff these two. Can you tell me the difference between them? Actually, it looks like it just scrolls them wrong. Oh, man. All right. I should probably just install Beyond Compare here because this is pretty crappy. And it's hung. All right. So, yeah, I guess this is what we're going to do. I use Beyond Compare at work. It's inexpensive. And since this doesn't work, let's just go ahead and say, look, you can afford it. Get a real comparison utility, I guess. So here's the download. Let's see, on Windows. So let me, well, I guess I don't care if it gets installed on this machine. Normally at work, I just use zip files because I like to put them into source code control, but this should be fine. All right, so let's try this in Beyond Compare and see if they fare any better. So in Beyond Compare, I'm going to say, look, this is the left side. This is the right side. Give me a comparison. And here we go. So you can see that these are actually different in terms of the order anyway. And it does look like they're actually legitimately different. Like, that wouldn't matter because that's just an order difference there. But it's then it starts to get to the point where I don't know about that part, right? But more importantly, I'm not sure I know why there would be that order difference, right? So the fact that those are there, I don't actually know. I don't actually know why that would be. So I think we definitely have an issue here. Furthermore, well, you know what? Let me check the partitions first. That's actually, I guess, what I wanted to do. So let's check the partitions first, and I'll refrain from comment until we actually do that. But yeah. Point being, looks bad. All right, so here is just a big old chunk, and it really does look like we're traversing a bunch of extra boxes. So like I see a bunch of differences on this side, and I don't see it on this other side. So it's like we're pushing boxes on that we shouldn't be in the partition traversal. So why is that? So what we're basically saying is that when we switch this to 0, and we come through here, we're pushing things on that we previously weren't. Now, what's weird about that, right? I mean, unless I'm missing something. What's weird about that is, if anything, this thing should push less. I mean, if there was a bug in this, it would push less things on. Right? So it's weird that, like, what we're actually doing is we're pushing more things on. How are we doing that? Like, somehow, sort of fairly soon, too. Right on box, so we push on 229. Is that in here anywhere? So we visit, wait, what? So this thing visits 229 twice. Right? Did you see that? There's one. There's two. What the heck? Oh, well, okay, but it's per array. So that's, yeah, sorry. I was freaking out there. Since it's per array, that's fine. I should probably put in like a marker for each time. So that we can look at that more carefully. Because, like, yeah, duh. If we only look at one array, then we would expect to see a partition only visited one time. But since we're looking at many arrays, you're going to traverse those root boxes a lot of times. All right. So how did we mess that up? So let's put one more assertion in here. Let's assert that we never accidentally process a non-leaf in the partition container. Right? In the partition loop. I'm assuming the answer is that won't happen, but I just want to see. And we can also actually turn this off for now, because we don't need to record it at the moment. So I guess I need a separate switch for these as well. So I'll make a thing called record raycast stack. Put that in here. And now I think we're good. All right. So if we're going to record the raycast stack, then we do. If we're not, then we don't. And again, no assertions. So really strange. This is like curiouser and curiouser. I feel like we've hit a stumper here. So somehow we are pushing too many things on the box stack, even though we never accidentally process something that's not a leaf, nor do we accidentally leaf process something that we never process something that is a leaf in the wrong time or is not a leaf at the wrong time. As far as I can tell, anyway. How many boxes are there? Let's start with that. So in here, excuse me, when we load, and we print out, like when we print out that summary, so like here, could we just say how many boxes do we take in? And how many boxes do we put forth? So basically, before we build the spatial partition, we would print this. So we're inputting 1488 and we're outputting 2550. So I guess what I would say is I am now thoroughly confused. I have absolutely no idea what's going on. So what that would imply to me, right? So like if we look at this, how the heck are we getting the numbers that we're getting? Like, okay, so let's just go up to the top. How do I go to the beginning of this file? All right, so here's line 0 of the file. Oh, or not. But these files are just too big. Like, no, I guess diff utilities just can't handle large files or something. Like, I'm having a hard time viewing this file at all. Tell you what. Maybe what we should do is make it so that if we're actually doing a profile run where we're doing the dumps, maybe we just only do like one of these so that we can make these smaller so we can see them better. I mean, I don't know what else to say. So like maybe what we do just to make this tractable, because even Beyond Compare is having trouble with it. So maybe what we do is in the raycaster, we basically say like, look, previously we were doing like tons of raycasting, right? We go through all these work orders and all this stuff. Maybe in the raycaster now we just say, look, stop dumping after the first time or something, right? So something like that, where we say, look, this is the end. It's like, oh, okay. Like if it's the end, then we stop. So we just say, look, there's a switch. I don't know. So there's a stack dump switch. These are actually enclosed in if statements. Right? And so when the raycast ends, we just say like, stop that. Stop dumping. And then the raycast end in the lighting code can just be, so we record a single raycast. And that way the file isn't huge, right? Because we only really care about one probably, as long as it's different, as long as it has a difference in it, then we're fine. So we can probably just do it that way, and that way we can not have this utility failure problem, right? All right, so we'll just say, look, at that point, we've cast array, so it's over. So like, don't worry about it. And then up here, we can just say, you know, it's defined in nothing. All right, one more time. So now if I rerun this, I should be able to go like, okay, first let's see which one we're on. So I don't remember. All right. So this is the new way, right? That'll dump the new way. Oops. No, it won't. Now it will. All right. So that'll dump the new way, hopefully. So now we should have like smaller files. So we didn't get any. So that ray didn't hit anything. Is the answer, apparently. All right, well, let's take this case just to see, right? So there's the new one, and let me now make it do the old one. So those operated exactly the same. So the answer is we do have to get to, excuse me, we do have to get to something. So maybe I'll do it this way. Right? We'll basically say, like, look, if the stack dump switch is at a certain level, like, hey, we'll do 16 raycasts and then we'll stop. Know what I'm saying to you? So let's try this one more time. And again, this is just to try to get the data down so we can actually look at it in utilities without them freaking out. All right, so there we run. We did recompile. So this is the old way. Here's the leaf boxes. Here's the partition boxes, right? Which again, I don't understand what's going on because we shouldn't, I didn't think partition boxes could ever actually be below the box count. So something's weird already. Like, I need to go look at how this stuff works because I obviously don't understand, right? I mean, 2548 is the root box, right? Which makes perfect sense. But these are the input boxes, so 1488, anything above 1488 is a partition box. Anything below 1488 is a leaf box. These are partition boxes coming from the old way of doing things. What are those? Obviously the wrong kind of box, right? Doing on there. Again, 1488 is the minimum. That's actually a leaf. Like, what is a leaf doing on there? Excuse me. So, like, that's just wrong. Yes, it's not a leaf container, but it's an actual leaf. So how was it not processed as just one of the iterator things? We got issues. And by the way, assuming that this is correct, is actually good. These are good issues. Because if there were bugs in the original routine of the traversal that we didn't know about, they could be causing artificial slowness that we can get rid of, right? This could mean that we have optimization fat in there that's just due to bugs, which would be fantastic. So let's hope that's actually the case. It might not be, but let's hope. All right. So I'll make sure I'm dumping these right. I mean, it looks like I am. So let's, you know what? I don't even want to do a comparison yet. I want to know what the heck is going on here with this. So let's find out in Splitbox, how is this working? So when we call Splitbox, right, we go through and we say, if the number of things that are, if the source count, right, is more than 4 boxes, then we're going to split the thing. We look to see if we can split the thing. And assuming that we could, right? So assuming that, like, we actually found a plane that splits them, then we split them, right? And if we split them into 2, then we record whether or not we split them or not. So if we split, meaning the things that we got input in, we split, we say, all right, whatever the box is that we came in with, it's going to become a leaf container or not based on that. So either it becomes a leaf container because it didn't split, so its contents are things you test against, or it clears the leaf container flag if the things in it are therefore, if it therefore is containing actual splits, right? Actual split partitions, right? And I guess the thing here is, I guess maybe it's the indirection table that's confusing me. And I wonder if this indirection table should even be here. So I kind of want to say that this indirection table just shouldn't even be here. So let's get, because that's probably what I'm seeing. So the reason that we're seeing these is probably because these are not the actual boxes, they're box indices. And you know, since we're doing such heavy raycasting on these things, having that indirection is just stupid. It's just an extra read into a table for no reason. I feel like we should just get rid of that. So let's pause for 1 second before we try to debug this any further and say, all right, stop the recording. That's not going to happen. Run the old routine, right? Make sure it's working, right? There's our old textual error we expected, right? 6.6 seconds. Let's just pull out that entire thing. So let's say that in the lighting now, we're not going to have U16 indices here. I also don't know what the heck the scratch A, B, and C stuff is actually for. Is that really necessary? How is this working? So what is that? How does that work? So it gets past a source and a dest, and they're like scratch buffers, and it goes through those and tries to partition them into 2 lists, right? So that all seems fine, actually. So I guess, just looking at this, right, so looking at this, I feel like it wouldn't be that hard for us to rearrange this to just work directly. So add box storage is the thing that we're thinking about, right? And it's this thing. And all we would really need to do here is say, let's move add box storage. So instead of ever, add box references would just not exist anymore, right? And if I remember correctly, like add box reference, if you look, the only times we do that is just to, excuse me, is literally only in the case where we're doing it here. So this could just copy the boxes, right, of each of the children. It could just say, like, let's copy those. And so we only have 2 cases. We have one case where we know we added the box storages here, and we could obviously add them symmetrically. Like, there, those are now in a row. So we know we have 2 children and they go right one after each other, right? Like, right? We could say, look, we know those are contiguous. You know what I'm saying? So we know that these two children would be contiguous. And we know that if we didn't actually split, then we can just copy the boxes to make those contiguous, right? So we could just add box storage as we go. So here in this one where we say it is a leaf container, we can just add box storage for each child, right? So like this. So in here, when we go like, let's go through the sources to this particular box, what we want to do is like get that box and just add the box storage for that box into our set. And then all the boxes would just be continuous, right? We wouldn't need indirect referencing for anything because all the references would be correct, if that makes sense. Excuse me. And off we would go. So another way to look at this would be like, look, the actually split case, which is here, we could actually just change this to a look if you didn't actually split. And then this comes up here, so we'd say, all right, in this case, we set everything, right? So in the case up here where we say, like, if we actually split the thing, we're going to leave and we're not going to do anything else. This stuff now becomes, like, determinative, right? So the child count here, like, is 2. We don't set these because, you know, it's continuous, right? So then the first child index in this case, because this is like an output box at this point, right? Wait, nope, it's not even quite that. I can just leave it like this now that I think about it. So during this, what we would do is we'd actually add a new one for the parent box, right? Entirely. So it's a little complicated to do it because just in order to make this routine still work the same way that it was before, but to stream them out directly, it's a little bit more work. Once you've added the children, you know that the children are added in order. So now you should be able to add the parent, and that parent should be basically in order as well. Right? So, excuse me. Yeah. So I think that's fine. Yeah, I think that's fine. The only thing I'm not sure about is the fact that as you're walking the tree, you use different indices. So in here, when you're getting these things out, this source set... Oh, but it's not, because it comes from here. Yeah. All right. So I think we're fine. So I think we can actually just basically leave this as is. And the only difference here is that instead of this, like the first child index bit here, the way that works has to change slightly. So when we do child box A, child box B, and the add box references, this part needs to change. And instead what has to happen is we just have a first child index and a child count here. So we need those to get set. So let's just set them where they actually happen. So in here, we'll just say, look, this is going to be 2, right? So we're just going to set this, like the parent box here, we're going to set. And then we need the first child, right? The parent box pack, first child index. That's just going to be this child box A at, right? So that's all we're doing here. You know what I'm saying to you? So that's all we need to set in that case. This case doesn't need to happen at all, right? This doesn't need to happen either. So then all we need to do is when we are a leaf container, all we need to do is just set these things up, right? And the way that we need to do that is we need to do add box storage for all of the boxes in our set, right? So we need to do, like, for add box storage, we would do, like, box count equals 1 or whatever, right? And then in here we would say, look, let's make sure we can fit that many in, and then you can add as many as you want at a time. So then what we would do is say, well, the child count is just the source count, right? We know it's a leaf container. The first child index is the add box storage of however many of these things we actually have, which is that. And then we just need to copy them. So we need to do like child index 0, you know, and these are 16s, I guess. Child index is less than the child count. And for each of these, we copy it in. So whatever the solution box is, child index, like so, right? That's going to be copied from the source box. So, you know, it's this. Actually, I guess it's this way. Might be the right way to do it. So we say, look, here's our sources, and each one of those needs to be copied into like one of the parent boxes. Oops. There's a bit of a misclick there. There we go. So now that streams out where we say, excuse me, we now have a compact list where we just say, look, we're going to stream these out in order. So now there's no box references ever. So the box reference concept would go away, meaning this right here would go away, I believe. And the get box concept would also go away, I think. So I'm going to try that real quick and just see if I can make that work. So in here where we do lightbox index, again for getbox, this would no longer use a ref. I mean, the other way we could do it, I suppose, is getbox could just work without the box table. So we could just do this, right? We could also assert that like solution, that like box index is less than solution box count, right? So what else? So in this case, when we add the root box here, again, we're not adding references anymore. We just add storage like this, right? I'm not sure we actually need to do anything else. Here's the child count equaling the source count. You can only have use 16 of those. I mean, we can assert the source count is less than, you know, U16 max, but it's not going to be, U8 max, sorry. Because we already said it had to be less than 4. Looks like we don't have a U8 max. Somehow? Yeah, we don't. No biggie. We've got one now. All right, and so now we have to see whether that works at all. I mean, it might be a total disaster. And we'll see. So, yeah, still looks buggy there, right? Like, that's not quite right. So what did we mess up wrong? Excuse me, what did we mess up there? Let's take a quick look. So, when we're actually pushing these on, and now we're just calling getBox, I guess let me just make sure all the places we're calling it make sense. So getting the root lightbox should be fine. Getting the child indices here, that should be fine. Same here. Same here. Yep. So all of those are what you would expect. The ref C there should be fine. Yep. Yep. So all of that should be fine. So let me see. So our split box must be slightly wrong somehow. So we pass the sources down here. How do we pass those? Because I'm not sure how this dest bit works here. So you can see that what we do is we loop through and we write out the refs into destination arrays, right? Yeah, so we pull out each box. And so I would assume that if we actually made it down to here, where, you know, if we actually split, we remove the leaf container. Whereas if we didn't actually split, we store it. The child count is going to be the source count that we were given. The first child index, we're going to add that many boxes, right? However many we had. Make sure that is right. Nope, that's wrong. So this is actually that, and we have to do the increment after, right? That was just a screw up there. So because the result is going to be what the box count was, that plus equals was not. Like, that'll give us the wrong result. So let me try that one more time. Okay, so now we're back to the correct textile error. So that's a good sign. And what we can see here is we saved some time again, right? So before we were running it like 6.6, I believe, pretty routinely. And, you know, we managed to drop down again. Like, you can look up back at our starting runs as we were working through those. We got down to 6.6, right? But we never had anything as low as a 6.4. So removing that table helps us too, right? So now that we've removed that table, we don't have those indirected box arrays. So now our lighting structure is also more straightforward. So we can, for example, remove the ref count, the box table, all of that stuff can go away. Now, since we flat load this thing, we can't just nerf them yet, but we can say like, hey, all of this now can be removed, right? So that entire box table and all of the box references would be removed. And furthermore, I can nerf them explicitly here so that I can check to see if anyone's actually doing anything with them and get rid of it. So this debug dump now is irrelevant. It doesn't have to happen anymore. This box ref count here can go away. It doesn't need to be there anymore. This check is not relevant because we don't need box references. All right. So that stuff can go away, and we can simplify our lives by just doing a recapture there, and off we go. So our 6.4 is now like, hey, we're actually like a full second faster on our test yet, and we haven't even really started to optimize this thing. Like, all we're really doing here is just the basic work of getting us into position to optimize. Like, we haven't really even looked at our performance counter numbers. We just got it working with VTune, but we didn't actually do anything yet. So, I mean, this is great. Like, this is good progress that's being made. We're just decrufting the routine. All right. So now we want to go back to what I was doing before, where I was saying, like, look, now we should be able to see those values and they should be clearer what's happening. So now let's actually take the dump. Let's actually take a dump and see what's going on. So if I build now with the old way of doing things, I should be able to score some traversals here that let me see what's happening. So there's a run. Here's the old way. And now we should see exclusively high numbers, and we do, right? So that's easier now because I can verify that there's no leaves in there, which I was just nervous about that. So this is the old leaf traversal. Here's the old partition traversal. Now let's go ahead and do another run where we do the new traversal, and let's see what that looks like. Because again, this is broken, we think, right? And you can see that the max textile error jumped up like dramatically, and we don't know why. Something's busted. So now let's take a look. Here's the new leaf box traversal, the new partition box traversal. And let's go ahead and diff those. So here's the old one. Here's the new one. And there's a very small difference. So it's interesting in that looking at these, you can see that the routine behaves fairly similar to what you would expect, except for one minor difference. Now, this is good because, again, it helps us to, if there's only a small number of differences, we can start to isolate into those differences. I do want to do one thing that's a little bit odd here. So I'm going to say source. I want to know who caused the addition to happen. So, like, what I'd like to see here is when we go and record a partition box, and I don't know there's really any way to do it, actually. So maybe not. It'd be nice to record who pushed it. You know what I'm saying to you? So maybe what we could do here is say, hey, when someone pushes someone on, we'll record that too. So like, we'll send the should push. We'll say who got pushed. And we'll go from there. So we know that we want to push down this box pack, right? So basically what we could say is like, here's the box pack that got pushed, and here's who pushed it. So we know the source index, right? Because we would have just written that out. So we can do a record partition push here, and the same would be true in our other case. We can do that here as well, right? So we could just, oops. Actually, we can just do this. And that way we have yet another piece of information. So record partition push, in this case, has two things. One is the should push, and the other is the pack. And this can just do like, look, if stack dump switch and should push, then fprintf partition box out, and we'll just do a little push line here. So that's the pack.firstChild index. And I guess we'll do it like this. Does that seem good? Let's see how that does. So inside Raycast, like, I'm going to go ahead and try taking the old one now. And again, just do another recapture here. So here's the old way of doing things. And so in the partition box traversal here, well, why didn't that push anything? Seems like that should have pushed something, right? Like, we're in this branch. Oh, whoops. That's in the wrong place. There we go. Try that one more time. There we go. So now we can see like who was doing what here. And I'll be honest, it looks a little weird. Like, what is happening with that oscillation? I guess those are multiple ray casts. So those rays didn't cast. So never mind. You know what? Let's add that too. Because I'm tired of getting confused about that part of it. So let's just put a blank line in there so we can see when the raycast actually ends. So there we have each ray. So like here's an example of a ray like 1490. It pushed 92 through 94. Then it did 91. That didn't push anything. Then it went to 92, right? So now we can see the stacked reversal a little more clearly. And again, that's the old way. And now let's go ahead and see what happens with the new way. So I'm going to go ahead and swap in the broken way, or at least we think it's broken. Maybe it's actually the one that's working properly and the other one's broken. We don't know. Right? So here's the new one. And now if I take a look at these two, so here's the old one, and here's the new one. Oh, whoops. I just want new leaf box reversal. There we go. New partition box. There we go. So if I look at this now, I should be able to see like where the push went wrong. So what looks like it happened is on box 1638, for some reason, this thought it needed to push the children of that box, but this didn't. Right? So I guess the only thing I'm not sure about, though, is well, no, this, I mean, yeah. So this should record both types of push. So if you were supposed to push, in either case, it records the push, whether it was leaf boxes or not. And so you can see here, like 1639 and 1638 both pushed, and then those pushes even pushed, right? Like there was actual results of those that went down. So we now know a specific person we could look at. Like we can look at 1638 explicitly if we want to, and see why that happened. The same would be true of 1844, it looks like. So something is happening with those that is like causing a push, and we don't know why. Like, why are those getting a push and only those, right? Fortunately, this is pretty easy to look at, I guess. So, I mean, it's just... $16.38. I mean, something like that. And I'm guessing that like, I mean, I guess I could just do this. So that would stop me in Remedy right there. And I can see, you know, what's happening, I guess. And the same would be true in here, so I can just do the same thing. Just right before the should push, you know, I can put that breakpoint in there. I guess I can do this even further down, right? And I'm going to go ahead and compile in debug mode here and verify that. I mean, I would like to just be able to not have to do this in release. So I'm going to verify that the same thing happens on both. I don't know that it will because there could be problems with that. So let me just first verify that this is true. So I'm in the case where the old way happens. I'm going to take a look and say, all right, don't quite do that yet. Run a trace and make sure the trace is the same. So there's the trace. Here's the old partition box traversal. And then here's that same one compared with itself. They're exactly the same. So in debug mode, I should be able to just reproduce this just fine. So if I now do this and run it under Remedy, like so, I should stop on the one we actually care about, right? So here's source index 1638. So if I actually clear this out and just look, there's source index 1638. And what we want to know now is like, all right, so we're assuming that any, like these numbers are wrong, or these are the correct ones, I should say, and they're what's wrong in the other one. So oops, any inside should push. So all of these are false, right? Nothing actually hit. The box that we're looking at, so if we look at the actual box structure here, so I just thought of something I want to check. Sorry to derail that train of thought. So when we push onto the other stack, we should check to make sure that the leaf count isn't larger than the total size we have, right? So like because we could just be overwriting that memory. Maybe that's all it is, right? So if you look in here where we actually create these, oh, this is garbage, right? We don't know that that's, well, no, it's not. Because if that's the total number of boxes there are, we couldn't actually push more than that, could we? But you see why we could have a problem there, right? So I think we do kind of want to at least validate that, right? So I'm not sure exactly the best way to do that because the box count itself has been modified at that point. So it's harder to have some way to record that. But I can just do this. Oops. So if I save the global max work stack depth here just for debugging purposes, right? then I can do an assertion here that it doesn't get over pushed, right? So, for example, in this case here where we push onto the leaf count, I can just do an assert that like the leaf count is less than the global max work stack depth here, right? And off we should go. Now, I will admit, oh, but I didn't file case it. So now if I turn this off, I should get, I should get an error in the non-light perf build that's undefined, and that's fine. And now when I run this, beautiful. Okay. So the problem is we were actually somehow generating too many box pushes. What the hey, man? So I wouldn't have thought that was possible since each one of those can have at most one child. I'm sorry, at least one child, or they wouldn't get pushed. So how the heck are we pushing more than the total number of leaves worth of partitions? Am I missing something there? Oh, wait, no, never mind. That was the debug break. Never mind. Everyone calm down. I was going to say that was surprising me. All right, so I'm going to nerf this real quick. We're not going to do the debug break. Because I was going to say that shouldn't have been the case. But let's see. Maybe it still is. So I want to see whether I ever hit that assertion. Right? This assertion right here. And doesn't look like we do. And in fact, I can probably verify that like here. So I come down here and you look at leaf count, right? You can see like the number of leaves that we get is like super low, right? It's just not that high. So I don't know what the maximum leaf count would be, but it's not going to be that big, I don't think. And so we don't actually ever hit that assertion. Okay. Good. Because I was like, you shouldn't ever be able to hit that assertion. It should be completely impossible to do so. All right, so we're not overwriting that, I don't think, although it's possible that we allocated too little memory for it somehow otherwise in this sort of hacked routine here, where we do the stack space. We malloc the max work, and we did. So I think that was it, right? Or no, we didn't. Why do I keep thinking that? I keep misreading that as the work count. So nope, totally fine. That allocates as many as we wanted. That's what we would expect. So yeah, I don't know. So let's go back to what we were doing before. I just wanted to check that and make sure nothing was weird there. So we'll pull out that assertion and this. I'll go grab the global max stack depth. There we go. And now we can put these back in. So let's just take a look now at 1638, box 1638 in both cases. So we can see why like one thinks we should push and one thinks we shouldn't push, because I have no idea why. So we'll look at this case first, and we'll just manually inspect the box and see if there's anything weird about that box, right? So here we go on box 1638. We can look here. It's like negative 37, negative 90, negative 28, 0605, right? I mean, I don't know. We could try to copy these values. I don't know if there's any way to dump the watch window. I don't know if George is watching, but a way to like dump the watch window would be pretty great. Like, know, save watch window to file or something like that. You know what I'm saying? So what I'd like to do is say, look, we know that all of this came out 0 in our reference case. So we're not going to push this thing on the stack. We know that the box looks like this, and so we should, in theory, have exactly the same results, right? And the pack, well, we don't care because it doesn't even matter what the pack is because we never push it. So we just want to know that these are the same. And so, like, that's not really what I want. So I really just want to know this stuff, right? And I guess I could just put it in a little, like, temp area somewhere. Like, yeah, I don't know. Like Notepad++, right? Here we go. And then here's Boxmax. And that's just so I can see if the boxes look any different, which hopefully they wouldn't, but, you know, what if they do? And then similarly, I can also look to see, like, the only other thing is, like, the ray origin and stuff, right? And the inv-ray-d, right? Like this stuff. And those should not change at all. Like those, no, if someone's like mucking with those, then we have a problem, right? So right. So the ray origin should be duplicated because it's multiple rays coming from out of the same origin. And then the ray direction should be, well, you know, so I mean, it's, I guess we'll copy that in as well. I don't know. I don't really think that's going to change, but I suppose we should just double check that it didn't. I mean, it couldn't because if these two changed, then everything downstream would change. So I really don't know what's up. So we got the box. We've computed these. Yes. Okay. So I really don't need to go any further. I know what's going on here. So we will actually produce different results. And the reason that we'll produce different results here is that the T max values, well, although, you know what? I guess I'm not sure why we produce different answers. But what's happening here is we aren't actually testing things in the boxes as we visit them. And so the result is that we will test more boxes because we push more leaves on to the stack. So I guess we really, yeah. So I guess now that I drill down to that, that does sort of answer my question, which is that it seems like you don't want to stream this because as you go down, you want to test the things in the closest box first, always. And if you hit something there, you don't want to test the other side. You don't ever want to go down it. All right. So I think I don't actually want to even drill down any further then. So that answers my question. Streaming is not happening because we need to actually early out, right? So that is over. Goodbye. You're gone. So actually what we want to focus on here is doing this sidedness in the correct way to early out. So I think that's really what we want. So what we want to do tomorrow, now I know what we're doing. Since we're doing KD tree probably, so we haven't really talked about not doing that. If we're going to go for the KD, what we want to do is test the near side of the KD tree first. If there's a hit, we just don't test the far side. So that's what we need to actually do, right? So we need to keep those bounds, right? So we do want to do depth first. We want to walk down all the way down, test the closest things, and only start testing further things out when they don't hit. So that's what we're doing tomorrow. That's what we're doing. I've declared it. I've declared it. That's what we're doing. Okay, so before, I'm not going to actually stop today. Oops, I got to get rid of those debug breaks. So before we stop today, I want to go create, I want to go back out the scratch buffer change, since that doesn't need to be there anymore, because we're not going to use it, right? So that's just gone. So let's go ahead and test this. Here's the debug mode. I'm gonna flip it to release mode in a second here. You know what? Let's just stop that. And I want to go into lighting and just say like, all right, so let's just get rid of this. That's gone. Goodbye. In the internal lighting core, this can now do the work solution set again. So this doesn't have to happen. And I think we're good now. All right. So let's run the lighting core. Looks about right. Let's run the actual version. Looks about right. Seems fine to me. Let me just see what our profile looks like. So, yeah, I mean, that looks like what we would expect. Yeah. So that all looks fine. We can do a brief Q&A. Wanted to let you know we have a is memory equal. Oh, so we do. Where is it? Memory is equal. So we do have that. So I just couldn't find it, I guess, when I tried before. So this doesn't have to do that. It could just do like memory is equal, right? And you can just pass it 2 buffers. Looks like I don't have exactly what I want though, because I need one that takes the counts. So I guess we'll leave it like that for now. Off topic, but I noticed your latest blog post. Oh, thank you. I probably forgot to set it. I manually enter the date on those because, you know, it gets generated and then pushed. Let me remind myself to fix that. I'll push a change today. All right. Why is it that software companies increasingly seem to not care about performance? So the reason is that, I mean, there's the reason that it happened, but I don't know if that's really what you want to know. The reason is because they can. Right? So previously what would happen is nobody would have used a piece of software if it took so long to type characters that, like, you know, like if you program software the way you program it today and, you know, the machine you had was a Commodore 64, no one could use that piece of software, so it wouldn't have existed. That company couldn't have sold software, right? But, you know, more or less what happened today in today's world is like users don't really demand much performance. They demand only very passing performance. So that's the end of it. If your users don't demand good performance, then companies can keep selling bad performance. And so I don't really know how to say it any other way than that. It's because companies can stay in business who ship poor performing software. That's it. If users stopped accepting low performance, then you would get high performance. Right? You have to look at software as the software you have is the software that can exist, right? So companies just generate software, and unless you are actively weeding out companies that generate bad software, you just have bad software. So at some level, it's just like, look, maybe someday people will start to demand performance. And maybe that happens because some companies start shipping high performance stuff and then people gravitate towards that. They're like, oh, why would I wait, 30 seconds for my freaking Facebook page to load when I can just use this other service that's instant? And then you get that service, right? But until then, you just won't, it's not going to happen. Do you have a Git repo for any of your code? So not really, no. I don't use Git or GitHub. The Handmade Hero source code is available if you pre-order the game. So like if you go to if you pre-order the game here, it comes with the source code that you can look at. There is a GitHub, a private GitHub that you can get access to if you've pre-ordered, but it's unsupported. So, like, when you pre-order the game, it will give you this screen, which basically tells you you get absolutely no support for the GitHub. So the only thing I actually guarantee you get is the downloadable source code, which is like you just click, it's like a zip file, right? But there technically is a GitHub, I just don't support it. People wanted it, so it's there. It gets automatically updated. So the GitHub for this source code is actually there, right? But it's private, because this is not public domain software. Right? This is like a commercial thing, right? About my question before the stream started, I am looking for a doubly linked list structure. And usually that's done through a structure with a first and last entry pointers. And those have a structure with a next prev and value pointers. Let's call this entry structure. In order to add an item to the end of the list, you need to create a new entry structure, set the prev pointer to the previous last entry, and update the last entry structure in order to have the next point to the new last item. Is there any other structure that does this without this prerequisite? Again, I'm sorry if I'm misunderstanding you, but I have no idea what you're asking. A doubly linked list is just a linked list that has next and previous pointers. I don't know what you mean by prerequisite. Obviously, you have to update the next and previous pointers when you insert something because they have to point to the new thing. So what is it that you're trying to avoid? If I insert an item, so if I insert item B after item A, I have to go change A's previous pointer to point to B. And furthermore, assuming that, you're keeping a doubly linked list, then if you have A and C that are in the list, and I insert B between them, A's next pointer has to point to B, and C's previous pointer has to point to B. So you have to update those two pointers, and I'm not sure what you're asking for. Like, how could you not update them? You would not have a properly linked list if you didn't update those two pointers on insertion, right? Are there any scalability, usability issues when using enums versus something like a hash table for indexing assets? Well, enums are more scalable than hash tables. So do you mean just usability? Like enums would be compact and perfect. So they scale perfectly. Whereas a hash table actually costs you something. It costs you the amount of time it takes to hash something, right? So enumerating your assets with a globally unique set of indices is like the fastest possible thing. Usability-wise, yeah, there are some issues, which is to say that you have to have a way of allocating those enums, and you don't want to leave like gaps in the enums, otherwise you waste memory in the table. So you do have a usability issue there. I want to say that the witness... Is John here? I don't think Naysayer's here, but if John's here, he can answer this question. I didn't look particularly hard at how the witness did their enum allocation, but I want to almost say the witness didn't even compact its enum list before shipping. Like, it was something John was going to do and then didn't even have to do because it just didn't matter. It wasted some memory, but no one cared. Right? So yeah, but he would be a better person. If he's streaming right now, we're just going to go raid him after this anyway. So you should ask John that question because he actually ships games on the enum method, not the hash table method. So he can probably tell you exactly what you want to know from experience rather than hypothesis. Do you know of some sane way of learning a bit of DX11 other than trial and error while scavenging information on MSCN? There's got to be a DX11 tutorial somewhere. How would you recommend writing assembly directly for a function if the compiler refuses to optimize it the way you want? Usually what you have to do is one of two things. Either you just have to make an ASM file, so you just write the function in ASM, or you just fuss with the C and try to get the compiler to eventually do the ASM you want, which sometimes works. Often it works. If you happen to be using a compiler that isn't Visual Studio, so if you're using Clang or GCC, those compilers actually have some inline assembler facilities, so you may be able to just put some inline assembler in there, and that can help tremendously. But Visual Studio doesn't support that because, you've seen how fast Visual Studio runs. Are you surprised that they don't allow inline assembly? I imagine the people working on Visual Studio don't even know assembly at this point. How important is it in game development and in general to be concerned with microarchitecture level optimizations and using metrics and CPU performance? Critical, I would say. I would say that basically, if you don't understand microarchitecture, you probably shouldn't be an engine programmer at some level. Maybe if you're just on an architecture side, just period. You should just know that stuff. How many lines of code are there in the HH project? Like 50,000 or something. It's like less than 50,000, I think. It's probably not even 15,000, maybe. I don't know. Don't we have clock on here somewhere? So 34,000 total lines, and that counts everything, I think. So, including like the not the raycaster, including like the art asset processing, like whatever, everything involved. If you do another programming discussion with John, do you think it would be valuable to do a discussion about entity systems? I mean, no. Like, John has said a million times, entity systems are stupid. Like, it's a waste of everyone's time, and I don't know why people harp on them, right? They're just... It's not a thing. VS19 has support for x86, but not x64 assembly. Why is it one but not the other? Oh, so I don't actually know the internal reason for this. I know what you're asking. Let me summarize this for people who don't know. So Visual Studio doesn't support inline assembly, but it used to. So it used to support inline assembly. And why does it not anymore? Well, the answer is because when they went from x86, the x86 compiler to the x64 compiler, that's where they lost the support. So if you switch back to the 32-bit compiler, you can actually have inline assembly back. But when you're doing a modern 64-bit build, you can't do it. I don't know why. I think it's because they didn't want to do the work. I think it's just pure laziness. They didn't want to have the code paths necessary to ensure that user assembly could be inserted into the back end and work. Thodura, I meant like what you guys consider is a good approach. Yeah, the point is, if you're thinking about entity code as a system, then you should stop doing that. That part of the code is the structure of your game. It should not be systematized. It depends on the game, and it should be like written in the way that makes the most sense for you to express the behavior of the game, which is inherently not systematizable unless your game is very generic. All right, looks like that's it for cues. Did we ever hear back from Mario Manzani about the W link list? Because I still don't feel like I actually understand the question, but I don't know if maybe that's just because I am thinking he's asking, or I guess I don't know if it's Madia is male or female, but they are asking a question about like updating pointers in a W link list, or whether they're asking about some other thing and he's just mentioning the pointers or whatever. I don't quite understand. And so I just wanted to make sure, is there an actual follow-up to that question that clarifies it at all, or what? Because that one I did not answer, but it's because I don't understand it. So I don't know if we could get a clarification in there. Oh, I think you're saying you think they wanted to know if there's something that acts like a doubly linked list that isn't actually a doubly linked list. So just like something that's easy to remove things from, I guess. All right. Well, I'm going to wrap it up. They can get back to me with a more specific question if they have one later. But all right. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you want to follow along with the series at home, you can always pre-order the game on handmadehero.org. It comes with the source code so that you can follow along with it. We also have a Kickstarter going right now for our comic. Be sure to check that out if you like comics. It's pretty easy to find. The banner should be on our pages at the top. You can just click through there, and it is here. It is funded, too, so if you back it, you will be getting a comic from Anna and I. When the Kickstarter closes, we will be sending it off to the printers. So that's about it for today. I'll be back here tomorrow now that I'm pretty sure I know what's going on in our loop in terms of what I want it to do, we can go ahead and do that. I'm going to go raid John's stream now. I don't know what he's doing over there, but we're going to go find out. So for those of you who want to stay tuned, I will not actually end the stream. I will go raid now. So see you folks tomorrow, and let's go raid John. Wait, what the heck? I'm not seeing anything on here, though.